One of the motivations that led us to study relativistic fields was to obtain relativistic forces, the thing that appears in the right-hand side of the dynamical law of motion. Okay, when this is subject to a force, whatever appears here will be a relativistic force. Now we have the opportunity of obtaining the form of one of these relativistic forces by studying the coupling of a particle to the electromagnetic field. This coupling will have to satisfy certain properties in order to be consistent. One of them that we mentioned in a previous video was that the new action will have to be reparameterization invariant. Remember that the action is described in terms of a generic parameter, evolution parameter, lambda, so we describe the world lines as functions, some functions x mu of lambda, and that the same physics should be obtained if we change lambda by another parameter, lambda prime, which is a function of lambda. Another requirement is that the coupling should be Poincaré invariant. Okay, then this already implies that probably it is much better to consider the coupling in the coupling x dot mu, which here is d lambda x mu, or this is supposed to be d lambda, than just x mu, because x mu is shifted by space-time translations, while x dot mu transforms really as a vector. Okay, we know how to construct Poincaré invariant objects by contracting indices. So if we use x dot mu and the electromagnetic field is described either by a mu or f mu nu, then the possibilities are a mu, a term like this, added to the action, or a term like this. Okay, we have to saturate all the indices, because otherwise, if there are free indices, we will not have Poincaré invariance. Now this is symmetric in mu nu, this is antisymmetric. This cannot be, because this is automatically 0. So essentially the only candidate is this one. Now the only problem that this candidate may have is that of gauge invariance. So we will study this a bit later. Okay, so if this is the term that we need, then the action will be, okay, we can describe it like this, a term mc square root of eta mu nu x dot mu x dot nu. This was the kinetic term for the free particle, and now a new term that requires a new coupling constant, which will be the electric charge divided by the speed of light, and then a mu x dot mu. Okay. Poincaré invariance is obvious by construction. Reparameterization invariance, I think we have mentioned this when we studied which possibilities, which possible couplings we could have in action for a particle, is also more or less evident, because we have a mu, dx mu, the lambda, and the lambda, and clearly if you change from lambda to lambda prime, the Jacobians that come from here, so the lambda over the lambda prime will cancel with the one that comes from here. So this is more or less obvious. And if I replace a mu by a mu plus the mu of chi, and this is contracted with x dot mu, okay, the new term that I get, this term will be the mu chi x dot mu. But using the chain rule, observe that this is just d chi over d x mu over d lambda. So this is just d chi over d lambda, and it is a total derivative. This means that if I replace a by a mu plus d mu chi, the difference will be a total derivative in the Lagrangian, and we know that the equations of motion that we will get are the same. Now, you need a word of warning. Okay, it is important to realize that this action is a function of the x mu's, the way I have written it. Okay, for the moment, this is just the only variables in this action are the x mu's of lambda. So what is a mu? A mu is a background field. A mu here is what is known as a background field. It will have some particular value, a mu of x. Okay, and this action will be good to study how a test particle with a certain charge moves in the background of this electromagnetic field. For instance, if this is the electrostatic field produced by a charge capital Q placed at the origin, this will be this divided by R. Okay, or if you want to use Cartesian coordinates, xi, xi. Then, when we use a particular, and this is only the zeroth component. So only when mu is 0, this gives you something, and the rest of the components are 0. So this is, the Coulomb field. So, okay, as we know, because we discussed this particular field breaks many of the Poincare invariances. For instance, the invariance under space translations. Okay. Now we will still have invariance under rotations, but under translations this is broken, and this is okay because this field interacts with the particle and there is momentum transfer from the field to the particle. Okay. And since this is a test particle, the field will not change when the particle moves or does anything. We are ignoring the back reaction of the particle on the field. This is why this field is fixed. It has a fixed value, and we don't expect it to change because of the motion of the particle. Okay. In order to study this, we will see later that we have to make a mu, instead of a background field, a dynamical field, a dynamical variable, and we will have to make a few changes. Plus, we should add the Maxwell Lagrangian, because we need something that tells us what is the dynamics of this field. Okay, so this we will do later. Okay, so this is formally Poincare invariant. What it means, because if we say that any background field will break Poincare invariance, what were we thinking about? I mean, although this looks Poincare invariant, this is not Poincare invariant the moment we replace this a mu by a particular configuration, and this is true. Poincare invariance here means just that if we replace a mu by the Poincare transformed field, and at the same time we transform the x mu's, the Lagrangian will have the same value. Okay, we obtain an identity. Just a mu prime of x prime, x dot mu prime will have the same value as this. However, the expression will be different. If we perform a translation, clearly the form of this field will be different. So the Lagrangian will be different, the form will not be preserved, and performing a Poincare transformation will not be a symmetry of this particular Lagrangian, at least with this field. Each field will break some symmetry, some subset of the Poincare group, and will preserve some, and then the quantities that are conserved will have to be studied case by case. Okay, for the moment, let's consider this action and let's try to find the equations of motion that follow from it. By using the principle of this list action, as usual, we will vary S. It is only the coordinates X that have to be varied, because we said that a mu is a background field that depends on the coordinates X. We have some particular value, but it is not a variable that we have to vary. Okay, so this will be minus, okay, setting C equal to 1, d lambda m eta mu nu x dot mu. We have done this like 100 times. We have already commuted the derivative and the variation of x mu. We have also cancelled a factor of 2 in the numerator and denominator. And the new feature is the variation of this interaction term. So we will have q, and now a mu changes because it depends on the x's. So we just apply the chain rule. We will have partial nu a mu, and then delta x nu. Okay, this is still multiplied by x dot mu, and a second term that I write below, which will be q a mu, and then again this is delta x dot mu, but the derivatives and the variations commute, so I write this. Okay, I have to integrate by parts now, not just this term but also this term. So let's do it. Okay, we have the minus sign, d lambda, and then we have d lambda m eta mu nu x dot mu. Sorry, I should change this by nu. There are two mu's here, so nu and delta x mu divided by this square root, and also the term that I get here. So this is q a mu delta x mu. This is the total derivative, and then minus d lambda m eta mu nu x dot nu divided by this square root, and also plus, okay, the minus is global here, a mu, sorry, yeah, a mu, and then with the q, and then delta x mu. And I'm afraid I closed this bracket too soon, because I forgot about this term, which is the one that I don't need to integrate by parts or anything, which is given by this expression. Okay, just because I have delta x mu here and I want to have the same thing, let me interchange mu and nu in this expression. So this will be delta mu, sorry, partial mu of a nu, and here this will be nu and mu. Let me forget about the total derivative, this one, because we know that the boundary conditions will set it equal to 0, and the only contribution are these two terms. So we have minus the integral over d lambda of minus, and I have the derivative of m eta mu nu x dot nu divided by this square root minus q, and then the derivative with respect to lambda of a mu using the chain rule will be partial nu a mu x dot nu. And then I have also this term plus q partial mu a nu x dot nu, and everything now is proportional to delta x mu. This is going to be the equation of motion. Let me still message it a bit, because I have partial nu a mu, partial mu a nu with different signs, and they can be collected into an f mu nu minus d lambda minus d lambda m eta mu nu x dot nu, and okay, I choose this plus qf mu nu x dot nu and delta x mu. So now this is clearly delta s over delta x mu. Well, if I do it carefully, then I have to include this minus sign, so I change the sign everywhere, and I get these equations of motion. So this is d lambda m eta mu nu x dot nu divided by the square root of you know what, minus qf mu nu x dot nu equal to 0. Now, in order to compare with the second law of dynamics, we need to rewrite this in a convenient form using the proper time as a parameter. In that case, this square root takes the value 1, and we have m, this eta mu nu here. Then we have x double dot nu. Well, yep. And on the other minus, so I put this into the other side, so this is plus f mu nu x dot nu. We can remove this eta from this side by multiplying by the inverse. Okay, so raising and this means raising this index up, and we get mx double dot x mu. Now the dot indicates derivative with respect to s. Okay, so this is q f mu nu x dot nu, and this is the relativistic force that a charged particle feels when it is coupled to the electromagnetic field. If you want to write this in a more conventional looking way, you probably want to choose the proper time instead of the proper time, the coordinate time. Okay, in that case, let me rewrite all this. You will have m dt, and here you have this factor 1 over a square root, which becomes, as you know, 1 over the square root of 1 minus v squared divided by c squared. We have done this several times, and this is the factor that is usually called gamma, and then the derivative of x mu with respect to t. Okay, and in the other side you have f mu nu and the derivative of x nu with respect to t. Okay, so for now we separate mu equals 0. So mu equals 0 gives you something which must be automatically satisfied. So this the t gamma equal to q f0 nu sorry, this would be f0, 0, but here it is f0i dxi over dt, which is vi. Then for mu equal I, you have m dt of gamma, and this is what you would call vi, q fi, then the component 0, okay, but dx0 over dt is 1 in units of c equal to 1, plus fij vj. So let's rewrite this in a more familiar way. So we can raise this 0 up, and this gives just ei. And if we raise this gives us a minus sign, and then this minus together with the minus that comes into the relation between fij and b, we have that a plus, and this is epsilon I j k vj bk. Okay, and this is the vector product. So if I write this in a vectorial form, this is gamma v, and maybe you want to put the m inside, because this is the conventional way of writing this. Okay, and this is q, vectorial way, I said, and this is e plus the vector product of v and b, and this is what is known as the Lorenz force. Which tells you how a particle with charge q and velocity moving with a velocity b in an electric field E and a magnetic field B, what is the force that it feels, and how the momentum, which is already corrected by this relativistic factor gamma, is modified. Okay, so you would have these two equations. And this is okay, much cleaner and elegant, the fully relativistic form of the equation. Now you might think that I have forgotten about this equation, okay, because it looks a bit strange and I don't know what it is, but remember that reparameterization invariance, what reparameterization invariance, being a local symmetry, leads to a constraint. This constraint we found before and has this form. Okay, and this is actually true, okay, of shell, and also after the action includes decoupling to the electromagnetic field. Okay, this means that, as you expect, there is one less independent equation of motion, and that you should be able to get this equation here, the one that I have forgotten, from these equations here, because it is not independent of them. Okay. Everything thanks to gauge symmetry. So now the last thing that we want to do is to consider an action for the full system of field plus particle. This action should be really Poincare invariant because you take into account the complete interchange of momentum. Okay, the momentum also gained and lost by the relativistic field, and therefore it is an action for in which a mu is also a variable. So this action depends on all these variables. It contains the Maxwell Lagrangian first, okay, and then we just add to it the action of the massive charge particle that we have written before. So this is x dot minus q a mu x dot mu. Now, there is an interesting way of writing this action which is helpful. Okay, we can take this term and put it inside of this volume integral. Okay, in this form. So we write this as minus a mu j mu, and the kinetic term of the particle just stays apart. Okay, eta x dot, and the j mu that plays that can play this trick. Okay, is j mu equal to minus q, the integral over lambda, this we cannot lose, and a four-dimensional delta, which these are the coordinates, the ones that appear here, and these are the functions of the word line, everything multiplied by x dot mu. So as you see, okay, this tells you when you look at the component 0, if you let's take lambda equal to the coordinate time, okay, this gives you 1, and you have delta at a charge q at the position where the delta is. Okay, so this gives you the charge density. The charge is completely localized at a point, and this is what the delta tells you. And when the particle moves, so the x dot i's are different from 0, the current, the components ji are proportional to the charge and to the velocity, and this current is also localized at the place where the particle is. So this would be the current of the particle. Okay, now you can find the new equations, for instance, how the Maxwell equations are modified. And you can see, okay, the first term just gives you this is the standard Maxwell Lagrangian in vacuum, gives you exactly the same. So you only get one contribution more from the second interaction term. This is j nu, and this equal to 0. So the equations that you get are partial mu f mu nu equal to j nu, and indeed this is the current. If again the consistency of this equation requires that this current is conserved, which is something which is a bit more subtle to check, but you can essentially check this holds except at the initial and final points of the word line, where the particle appears in space-time and disappears. So I said at these 2 points this is satisfied as you expect, and J0 has the interpretation of charge density. If you integrate it in space, it gives you the charge and so on. So everything fits beautifully, I would say. The equation of motion for the particle is exactly the same as we wrote before. It has the Lorenz Force term, but the difference with between this case and the previous case is that in the other case the Lorenz Force this is given by some functions e of x which have been given from the beginning. This is the background field in which the test particle moves. Here the particle is not a test particle anymore. When the particle moves, this or doesn't move, but just the particle is there, it creates a field, and on the other hand the particle fills the field, okay, in this way. Of course this classical action has a lot of problems, okay, because there is the problem of the self force of the particle at the place where it is, and it is only quantum mechanics and quantum field theory that solves these problems. But nevertheless, this is quite interesting and quite elegant.